on this section 4.5 is going to be a continuation of the word problems from section 4.4, solving exponential models, using logarithms, which is what the last part of section 4.4 was about. So we're going to continue with the same thing. We're going to start with a couple of questions here. Let's begin with this. This problem states that the exponential model A is equal to 225.6 times e raised to the 0.031 t describes the population A. So once again, the population is represented by A, okay, of a country in millions. And then it says t years after 2003. That means that, let me just give you an idea. T years after 2003 means that on the year 2004, t is equal to 1. On the year 2000 and let's say 13, t is equal to 10. So t is going to be representing the number of years after 2003. Okay, so with that said, now the question is, we want to use that model to estimate the population of the country in 2003. So what is the value of t in 2003 if t is the number of years after 2003? It's going to be t equals to 0. So what we're going to do to find the value, we're going to go into this function and we are going to replace the t with the 0. Then I'm going to mention something important about these models for you to remember. Okay. After this, I'm going to go over the general formula for you. So A is equal to, so let's go ahead and put that in the calculator and find the solution for this. So we have 225.6 times e, second ln, raised to the power of 0.031 times t, which is 0, and then we close the parentheses. That gives us 225.6 as an answer. So that means there's going to be 225.6 million people in the country, in that country, in the year 2003. That's what it tells us. But wait a minute, don't we see that this value 225.6 isn't it the same thing as this number that we have in the front? Now, and that is for a reason. Let me go back to the actual formula. The formula for exponential growth and decay, it is A equals to a of 0 times e raised to the k times t, in which the a represents the future amount and the ace of 0, this is referring to the following: the amount at time equals to 0. That's what the little 0 that you see there is. The amount at time equals 0, which we call, it's another word for the initial amount. And that's exactly what we were looking for in this problem. Since we were looking for the population at t equals 0, that means the initial population, and that is always represented by the ace of 0, which is the number in front of the e in my function. Okay, so then you see that the k represents the rate and the t represents the time. So we kind of went over this model a little bit in section 4.4. This is just a continuation. Okay, so now we're going to get into the next problem. Let's talk about this one. It says that prehistoric cave paintings were discovered in a cave in France. The paint contained 10% of the original carbon-14. Use the exponential decay model A equals a of 0 times e raised to the negative 0.00012 t to estimate the age of the painting. This is what the question is. Estimate the age of the painting. That means we need to find the value of t in this model. So there's only a couple of things, one little thing that we know from this function that they give us right here. Well, they give us the rate, that is a true fact, but not only that, they give us one more thing. They tell us that the paint contained 10% of the original carbon 14. So just know that whenever we talk about the initial amount, which is my A sub 0, that is 100%. Okay? So this 10%, it is talking about my value of A, which is the future amount. Okay? So this future amount is going to be 10%. 10% is going to be 0.1 or 0.10. Of means times the original amount. When I say the original, means the initial. Initial is represented by A of 0. So that's another way of representing that sentence. When I say that the paint contains 10% of the original amount, that means that the future amount is going to be 0.1 or 0.10 of A sub 0. That means 10% of the initial or of the original. So we already know right here that the A is equal to 0.1 A sub 0. So we're going to replace that into the A. 0.1 A sub 0 equals to A sub 0 times E raised to the negative 0.0001 to 1 times T. Now, since we're looking for the T, and the T is on the exponent, then this is an exponential equation. And remember, from section 4.4, there's a process that we need to follow to solve exponential equations, and that is the following. Give me 1 second. So this is what you see right here. I copied and pasted the process that you use to actually solve exponential equations when you're solving for a variable on the exponent. So that's exactly the process right here. This is from section 4.4. The first step in the process right here was for you to isolate the exponential expression. What does that mean? That whatever the base is raised to whatever the power is, you need to leave it by itself on one side of the equation. That's what that means. Now right here my base is E and my power is negative 0.0121t. This is the exponential expression. So what I need to do is I need to isolate it. I need to remove the A sub 0 from the front. So by dividing it on both sides. So, and that's going to give us, the A sub 0 is going to divide out on both sides. So we're going to end up with 0.1 equals to E raised to the negative 0.0001 to 1 times T. So now the exponential expression is isolated. Okay. The second step, as you may remember from the process, is that you need to put logs or natural logs on both sides. And I recommended on section 4.4 that you use natural logs. So I'm going to take the natural log on the left side and the natural log on the right side. So that's what I did next. Step 3 in the process. Remember that natural log of E basically is going to disappear. Natural log of E raised to some power x is just going to give me that exponent x. Right? That's the definition right here. Okay, that's what's going to happen. So this is going to, ln of E basically disappears and just gives me negative 0.0001 to 1 times T is equal to ln of natural log of 0.1. This is my step 3. And step 4 and last, what I need to do is I need to leave the T by itself. Solve for T. Now, how do I solve for T in this equation? I need to divide both sides of this equation by negative 0.0001 to 1 to get rid of that number from both sides. And that is going to leave us a T by itself. So in order for us to find the approximation, what we need to do is we need to put that in the calculator. That's how we can find the approximation for the solution. So we're going to go to the graphing calculator and we're going to put everything in. So we have ln of 0.1, then we close the parentheses, and that is divided by negative 0.000121. And that gives us 19,021.6. So they ask us for the age of the painting, so the age must be rounded to the nearest year. So we would say 19,029.6 will be 19,030 years. So we can say that this painting is going to be, it is approximately 19,030 years old. This will be the solution for this problem. So whenever we need to solve a problem in which we need to solve for the variable on the exponent, then keep in mind this is going to be the process that we always need to follow for those cases. Now, we're going to increase the level of difficulty for the question. Now we are going to work on this one. This is about the half-life. It's another special situation that we're going to encounter. So this problem says that the half-life of a certain tranquilizer in the bloodstream is 34 hours. How long will it take for the drug to decay to 81% of the original dosage? So, first of all, we're going to look at the first sentence. So we're going to use this model, but you see that now they don't give us anything on the model. That's going to be the problem here. So, in order for me to know basically how much something is going to increase with respect to time, or how much something is going to decrease with respect to time, I need to know, first of all, how fast is that something either increasing or decreasing. And that is represented by the rate, K. In this problem, we are not given the rate. So the first step in the process here is that we need to find that rate. Okay, so we're going to find the value of K. So what we know, it tells us that the half-life of a certain tranquilizer is 34 hours. So that means that after a time of t equals to 34, the future amount A, it is going to become, half-life means that it's going to become 50% of the original value. So that would be 0.5 or 0.50 of A sub 0. That's what it means by the half-life. That the future amount or the future value of anything that is given is going to become half of the original value, or 50% of the original value. Okay? So then on this function we already know what A is. A is 0.5 A sub 0, and we know that it's gonna take, whenever the A becomes 50%, it's gonna take a time of 34 hours right here. That is the t. So that is going to help us to find the value of k, which is the first thing that we need to do. So how do we solve for k? Since it is on the exponent, then we have to follow the same strategy. We need to solve it as solve this exponential equation. So we need to treat it like that. Okay. So we're going to follow this process again to solve it. So the first step in the process here is that we need to isolate the exponential expression. Remember, the exponential expression is whatever the base raised to whatever power must be by itself on one side of the equation. My exponential expression is the e raised to the k times 34. So what I need to do to isolate it, I need to divide the a sub 0 on both sides of this equation. And the a sub 0, which is my original amount, is going to be divided out on both sides. So we're going to end up with 0.5 equals to e raised to the k times 34, which I can rewrite it as 34k. So now the exponential expression is isolated. Second step in the process, we need to put natural log on both sides. That's the strategy we need to follow. So we're going to say ln of natural log of 0.5 equals to the natural log of e raised to the 34k. Then step number 3. What did we say it happens to the ln of e? The ln of e just disappears from the equation, so that just leaves me with 34k equals to the natural log of 0.5. So that's my step 3. And step 4 and last, I need to solve for the variable k. How do I solve for k? By dividing both sides by 34. So then we already know that k is equal to ln natural log of 0.5 divided by 34. That's the rate. Okay. Now what I am going to do next is that I'm going to put it back on the equation. Okay. This is my original equation right here. So now we can say that my new equation with the k that we found, it is going to be a equals to a sub 0 times e raised to the k, which is ln of 0.5 divided by 34 times t. This is going to be my equation. Now we know the rate. So now we can answer the question for this problem. Now let's go back to the problem on the top. What is the question? The question says, how long, so this is, I'm going to highlight the sentence. How long will it take for the drug to decay to 81% of the original dosage? How long means we want to find the time that it takes, T, for the future amount of the drug to become 81%, which is 0.81 of means times the original dosage, which is ACE of 0. So we want to find the time T that it takes for this A to become 0.81 of ACE of 0, basically. Okay. So we already know that what A is. A is 0.81 times ACE of 0 equals to ACE of 0 times E raised to the ln natural log of 0.5 divided by 34 times T. So we're going to follow the exact same process that we have right here to solve that for the T, because you see that the T is on the exponent again. So we need to first isolate the exponential expression, which is the E raised to that power. That is my exponential. So to isolate it, we're going to follow the same process, which is divide the ACE of 0 on both sides of the equation, and it's going to divide out on both sides. So it's going to give me 0.81 equals to E raised to the ln of 0.5 over 34 times T. Second step in the process. Now we're going to take, well, I'm just going to point out to it so you can follow. Second step in the process is that we're going to take the natural log on both sides. Okay, so this is going to look like this. Natural log of 0.81 equals to the natural log of E raised to the ln of 0.5 divided by 34 times T. Step 3. The ln of E disappears from the equation. So this is going to be ln of 0.81 equals to ln of 0.5. I was going to put something else. ln of 0.5 divided by 34 times T. And all we need to do now is we need to solve for T. That would be the last step on the process. So to solve for T right here, we need to, first of all, that 34 that is dividing, I'm going to multiply the 34 on both sides, right here. So that way I can get rid of the 34. So that gives me 34 times the ln of 0.81 equals to ln of 0.5 times T. And then to get rid of the ln of 0.5, I am going to divide it on both sides. So I divide the ln of 0.5 on both sides. This is how we're going to find the time. So then we have to put it in the calculator, okay, to find the time. So we're going to put that in the calculator, and we're going to get the following. So it is 34 times the natural log of 0.81. Press enter there. And that divided by the ln of 0.5 and close the parentheses, and that gives me 10.3. So what does this mean? That it is going to take approximately 10.3, the time is in hours, 10.3 hours for this tranquilizer to decrease to 81% of its original dosage in the bloodstream. So, now we're going to cover another type of model. The next type of model is going to be called a logistic growth model. This is basically a model for, an exponential model that has a limited growth. That's what we call it. What does it mean by limited growth? It is a model that it grows, but after some point in time, it reaches its maximum. It reaches a limit. So when can we use this as an example? Let's say, in a disease. So if a disease or an epidemic disease starts spreading in a community, when is it going to stop, or is there anywhere that it could stop? If it, let's pretend that it is not controlled. So it's going to stop whenever it reaches the maximum population, basically. So this is basically one of the situations in which we can use that model, the limited exponential growth. There's a couple of things that one little thing that I want to mention on this model that is important. The C on the numerator right here represents what we call the limiting size. The limiting size basically means the maximum amount that that model can hold. So if we're talking about population, then that C on the top will represent the maximum population of that community, or whatever it is that the problem is about. Okay, that's what the limiting size means. Okay, now the A represents the future amount as usual, and the B represents the rate, and the T is the time, so that doesn't change. That A does not have a meaning, okay, on the formula. It's just part of the formula on the logistic growth models. Now, let's go ahead and start with the next problem. We're going to answer this question next. It says, oh, no, I don't like that, so let me take that off the way. So the problem states, the logistic growth model at the right describes the number of people f of t who have become ill with influenza t weeks after its initial outbreak in a particular community. That's what the problem states here. So I'm going to copy the formula, okay, so you can all see it better. Okay, so the logistic growth model right here at the right describes the number of people f of t who have become ill with influenza t weeks after its initial outbreak. Okay, so 102,000 over 1 plus 4,300 times e raised to the negative t. Now the first question in this model is going to be letter A. How many people became ill when the epidemic began? So when the epidemic began, it will be when the t is equal to 0. So initial, it is talking about the initial amount again. So when it's talking about the initial amount or beginning, that means when t is equal to 0. So in order for me to find that, I need to replace the t with the 0 and find the value. So 102,000 divided by 1 plus 4,300 times e raised to the negative t, which in this case the t is a 0. And we need to put that in the calculator to find the value. So we're going to do 102,000 divided by, now I suggest that you put the denominator in parentheses, otherwise you're not going to get the correct answer. 1 plus 4,300 times e raised to the negative t, which is going to be a 0, and I'm going to close the two parentheses, and that gives me 23.7, which is about 24 people. We need to round to the nearest person because we're talking about population. So approximately 24 people were ill when the epidemic began. That's what the question, answer for question A is going to be. Question B. Just in case anyone wants to see the calculator, there it is. Now, question B. How many people were ill by the end of the 4th week? That means when t is equal to 4, because t is the number of weeks. So we're going to replace the t with the 4 in this function. So it would be 102,000 over 1 plus 4,300 times e raised to the negative, and the t is going to be replaced with the 4. So we're going to estimate the solution again. So we're going to go into the calculator, and we're going to replace the t with the 4. So it would be 102,000 divided by, open parentheses for the denominator, 1 plus 4,300 times e raised to the negative 4. Close the parentheses, and we get 1,278.88, which we're going to round it to 1,279 people. So that means that after 4 weeks, there were 1,279 people ill with influenza in this community. And last but not least, letter C. What is the limiting size of the population that becomes ill? Limiting size means what is the maximum population that becomes ill. And remember, the limiting size or the maximum is given by this number on the numerator. So the limiting size of the population, or the maximum population that can become ill, is 102,000 people. And that would be the answer for letter C. Now, we're going to talk about the next model. It is also a logistic model, but this is what the question is going to consist of. So we're given a logistic growth model for world population, f of x in billions, x years after 1950, is given by the function f of x equals to 12.57 over 1 plus 4.11 times e raised to the negative 0.026x. Okay. According to this model, when will the population be? 8 billion. So let's go ahead and get started with this. So the world population is represented by f of x. And x is going to represent the number of years after 1950. So we kind of went through one of these models before. So that means that if we want to find the population, let's say in the year 2000, that means that x is equal to 50. If we want to find the population in the year 1960, then x is equal to 10. So x is the number of years after the year 1950. Keep that in mind. So the question is, according to this model, when? What is it asking? Or the time. Will the population be 8 billion? What is the 8 billion? The f of x. Remember that the f of x represents the world population. So we want to find the t when f of x is equal to 8 in this model. So we're going to go to the model right here. I'm going to write it down. It says f of x equals to 12.57 over, then it says 1 plus 4.11 times e raised to the negative 0.026x. And we already know that f of x is equal to 8, so we're going to replace it with an 8. So 8 is equal to 12.57 over 1 plus 4.11 times e raised to the negative 0.026x. And I forgot right here that the time is measured with the variable x in this problem. So let me correct that, because I put t. So now on this problem we're using x. Now if you want to change it to t, it doesn't really matter. So there is no difference. It doesn't make a difference which variable you actually use. Now in this problem we're looking for the value of x. So, and you see that the x is on the exponent. So that means that we need to use the process for solving an exponential equation, which is this. We need to use this process over again. Okay, I'm going to put it a little bit lower because I'm going to be referring back to this all the time. So the first step in the process of this method is that we need to isolate the exponential expression, meaning that the base raised to whatever power must be left by itself on one side of the equation. Now what is the base here? The base is e and the power is this. So there is a lot of things that we need to do in this problem so that we can leave that e to the power of negative 0.026 by itself. So first thing is that we need to move it to the numerator, and in order for us to do that, we need to multiply that denominator on both sides of the equation. So the 1 plus 4.11 times e raised to the negative 0.026x needs to be multiplied on both sides. Okay. So right here, this is going to divide out. And so now we moved it to the left side, right? So we're going to be left with 1 plus 4.11 times e raised to the negative 0.026x times 8 equals to 12.57. Now, if I want to leave that e to the power of negative 0.026x by itself, we need to first get rid of that 8 on the outside. To get rid of it, we need to divide the 8 on both sides of this equation. So if I divide the 12.57 by 8, that's going to give us 1.57125. I'm going to write it the whole thing. Do not round. 1.57125. And that is equal to, that divides out here, to 1 plus 4.11 times e raised to the negative 0.026x. So we still need to isolate that e. So there's two more things that we need to do to isolate it. The first thing is going to be that we need to subtract the 1 from both sides, right here. So that will give us 4.11 times e raised to the negative 0.026x equals 1.57125 minus 1 is 0.57125. And then to leave that e by itself, there's one more thing that we can do. We can divide the 4.11 on both sides of this equation, and now the e is completely by itself, which is my exponential expression. Okay, I'm going to leave it like that because I think if I divide it, it's going to make it worse. And remember that you cannot round. Okay, so now it is isolated. So that was my step 1. It is already isolated. Okay, so we did a lot of steps here to be able to isolate it in this problem. Now, what is the next step in the process? In order for me to get rid of the e, we need to put natural log on both sides of the equation. Okay, so we're going to put natural log of e raised to the negative 0.026x equals to the natural log of 0.57125 over 4.11. So that was my second step in the process. Put a natural log on both sides of the equation. Third step in the process, the natural log of e, remember, it disappears from the equation, it simplifies. So that leaves me with negative 0.026x equals to the ln of 0.57125 over 4.11. And that is my step 3. Step 4 and last, we need to solve for x. How do we solve for x in this equation? By dividing both sides by the negative 0.026 on both sides. And that is going to give us the x by itself. So the last thing that we need to do to find the time breadth there, we need to estimate it using the calculator. So that's what we're going to do to finish this problem. So we're going to have ln of 0.57125, and that divided by 4.11, close the parentheses, and that is going to be divided by negative 0.026. And that tells us 75, which is about 76 years, right? 76 years. But the question is not after how many years. The question is when will the population become 8 billion? We know that after 76 years, the population will become 8 billion. But after 76 years, from what year? From 1950. Remember that x is the number of years after 1950. So that means that we need to add the 76 years to this year, and that means that the population will become 8 billion in the year 2026. And that is the answer for this question. There is one more question that we need to do, and the last one is going to be a different type of model that we're going to cover. So it is called Newton's law of cooling. This is going to be the last type of model that we need to discuss. Okay, Newton's law of cooling. So it tells me that there's only one little thing that I don't like on this formula. So this negative right here from the formula, I'm just going to get rid of it. I'm just going to put KT. So over a period of time, so if I have an object, like anyone that is in baking, for example, if you want to know basically how long is it going to take for an object to decrease to a certain temperature, so we can calculate that, or for any object, how long is it going to take for any food or anything that we boil or cook to actually cool down to a specific temperature. Now, there are several factors that, one of the main factors that is very important in this cooling process is going to be the room temperature. That is given, if you look at this formula, the room temperature is given by the C in that formula. So I'm going to give you all the components of this formula first. So I'm going to write it down. So T equals to C plus T sub 0 minus C times E raised to the K times T. Now that C represents the room temperature. that T sub 0 represents the initial temperature of whatever object. And the T on the left side, that T is going to be the future temperature. And of course, we already know what the other two variables are. K represents the rate, and T represents the time. Those stay the same. Okay. So first of all, you see that on this problem, we don't know the rate again. So if I want to know how long something is going to take to cool down, I need to know how fast is it cooling down with respect to time. So we're going to find that out first. Okay. So we're going to find K. That should be the first thing if we're not given the rate. So what we know is this, that a cake removed from the oven has a temperature of 225 and is left to cool in a room that has a temperature of 75. So we already know that the initial temperature of that cake and the room temperature, it is 75. So we're going to put the C, it's 75. The T sub 0, that is the initial temperature of the cake, which is 225. So these two numbers, which is the room temperature and the initial temperature of the object, those are constants. Those are not going to change. Okay? Whatever was the initial is always going to be my initial. Whatever is the room temperature is, that is my constant room temperature. Those two do not change. Now, one thing that we know is this. It says that after 20 minutes, the temperature of the cake reduces to 150. What does it mean? That when T is equal to 20 right here, the future temperature T on the left side right here is going to become 150. So we're going to use this idea to find the value of K. So let's simplify this a little bit. So we get 150 equals to 75 plus 225 minus 75 is 150 times E raised to the K times 20. Now, one thing is for sure, and I want you to keep in mind, and I said that before, this 75 and this 150 here will not change, because that is my room temperature and my initial temperature. Those are going to stay constants. Okay? Alright, so how do we solve for K in this problem? You see that the K is on the exponent. So since the variable is on the exponent, then we need to solve for the exponential equation by using this method again. That's what we need to do to solve it, right? This process again. So the first step in the process here is that we need to isolate the exponential expression. In other words, leave the base, whatever the base is, raised to whatever power by itself on one side of the equation. So that would be my E raised to the K times 20. So how do I leave it by itself? First, I need to subtract the 75 from both sides right here. That gives me a 75 equals to 150 times E raised to the K times 20, which is just 20K. I'm just going to rewrite it. And then we need to divide the 150 on both sides, so we can leave that E by itself. So 75 divided by 150, it's going to be 0.5. Equals to E raised to the 20K. So we already isolated the exponential expression. That was the first part of the process, to find that K. Number two, we need to take the natural log on both sides of the equation. So we're going to say natural log of 0.5 equals to the natural log of E raised to the 20K. That's my second step. Step 3 in the process. We need to eliminate the ln of E. Remember, that's what's going to happen. ln of E is going to be eliminated, so we're left with 20K equals to ln of 0.5. That is my step 3. And step 4 and last, I need to solve for K. How do I leave the K by itself? Dividing by 20 on both sides. So K is equal to the ln of 0.5 over 20. Do not use the calculator yet, because this is not my final answer. This is just part of the process. Okay, we're still not finding the final answer. This is just the rate, K. So I'm going to rewrite my equation. Remember that we mentioned that on this formula, the 75 and the 150 are not going to change. So I'm going to write an equation. This is what my equation is going to look like. T equals to 75, those are my constants, plus 150, that is also my constant, another constant, times E raised to the K. We already know what K is, and that is the ln of 0.5 over 20. That is my K times the T. This is my equation for this model. We know that this, whatever this cake or whatever this baking item is, we baked, what is it? A cake. We baked a cake. It is the temperature of that cake, it is decreasing at this rate. Okay, this is the rate at which it is decreasing. So what we need to do is now we need to answer the question that follows. Look at the question. The question is this. What is the temperature? What is the temperature of the cake after 40 minutes? So what is the temperature? We're looking for T when the time is equal to 40. That's basically what we're looking for. So we're looking for the value of the capital T. So T equals to 75 plus 150 times E raised to the ln of 0.5 over 20. And then the time is going to be 40. So times of 40. And we need to put this in the calculator to estimate the temperature. And I don't know if we need to round, but let's go ahead and round to the nearest degree. Okay, let's go ahead and do that. Round to the nearest degree. So we're going to put 75 plus 150 times E raised to the power of the ln of 0.5 over 20 times the 40. And now we can close the parentheses there. And that gives us 112.5. Well, I don't think we need to round, so because it's only one decimal. So the temperature of the cake after 40 minutes is going to be decreased to from 225 is going to go down to 112.5 degrees Fahrenheit after 40 minutes. And these are all the types of models for exponential models that we can talk about. We have the logistic growth models. We have the regular exponential growth models or decay models that follow the formula A equals A sub 0 times E raised to the K times T. And we have Newton's law of cooling that we just did on this part. And that concludes section 4.5.